All right, so before we got into the examples, I just wanted to do a little bit of a review, a quick refresher on the actual steps for graphing exponential and logarithmic functions. So this is just a basics. Maybe this chart is more confusing to you. Maybe this will clear things up. I don't know. We'll see how it goes. So this is the basic parent function here, right? F of x equals a. A can be positive or negative. Times b. Remember, b can't be equal to 0, has to be, or can't be equal to 1, has to be greater than 0. C also could be positive or negative. X, h could be plus or minus, k could be plus or minus. Okay, we always start with our parent function b to the x. This is always what you start with. Whatever is being raised to the exponent is your base, and your parent function is just that to the power of x. Okay. And then what you do with that is you input negative 1, 0, and 1 into that function. So we first do, this is b to the negative 1. This is b to the 0. This is b to the first. And those give you your starting points. If you were to plot those points, you would be graphing this function. Okay, and then we apply our transformations where we do the horizontal transformations in reverse PEMDAS order, doing opposite operation, and we do the vertical transformations in PEMDAS order, and we do the operation it says, right? So this one says minus h, we added h to our x's. So we simply took our x coordinates and added h, even though those look like, I'm going to zoom in real quick and edit those. Make them look like actual h's here. All right, there we go. That's maybe a little better. So then I take my y coordinates and I multiply them by a. Okay. If it was a positive a, I multiply by positive a. If it's a negative a, I multiply by negative a. That would just reflect it. So now I have this set of points, and I apply my last transformations. These are the most amount of tables and transformations you will ever have. If there wasn't an h here, we would just skip this. We just wouldn't do it. We'd start with doing x divided by c. The important thing is that you do the x's in this order and the y's in this order, right? They're two completely different coordinates and sets of points, so it's only important that we do the y's in this order, the x's in that order. It doesn't matter that you're doing, these at the same time. If there wasn't a horizontal transformation, sure, you could start off and do these at the same time. It's more a matter of the x's have to go in reverse PEMDAS order and the y's have to go in PEMDAS order. Okay? And then I get my horizontal stretch or shrink, divide by whatever c is. Again, if it's negative, divide by a negative c. And then if it says plus k, I add k. If it said subtract k here, then I would do y minus k, right? For vertical, you always do what it says. Okay, the horizontal asymptote is always changed by vertical transformations. Okay, so stretching and shrinking 0 is not going to do anything. And then when you add k, which means that your horizontal asymptote is always y equals k. Your domain is always negative infinity to infinity. There's no restrictions on what you can input into a exponential function. And then your range is going to depend on your asymptote, if it was reflected or not. So if it was vertically reflected, then it's going to be going down forever, so it'll be negative infinity to your asymptote. If it wasn't reflected, if it's going up forever, then it's just going to be your asymptote to infinity, right? Because the lowest it goes is the asymptote, and then it goes up forever. Okay? For log functions, it's very, very similar. Notice this part is the same, right? These two parts are exactly the same, whether it's exponential or log functions we're dealing with. The order you do them in, the fact that you do opposite operation for horizontal, given operation for vertical, all of that's the same. The only big difference is how we start this off, right? We start this off by still looking at the base, and then whatever the base is, you plug into this parent function, but we can't really put inputs into a log function. It doesn't work that way. So we have to change it to exponential form, which is something we're comfortable with. But then notice our exponent is y. So now we're plugging -1, 0, and 1 into our y coordinate, right? This would say b to the -1 equals x. B to the 0 equals x. B to the first equals x, right? We're going to have the y coordinates be what we input into so that we can actually get an output. So those are our starting points. Once you get these starting points, you're done looking at it in exponential form. You are back to the log form, and that's where you're getting your transformations from. Okay, so when we're adding h to the x's, that's happening to these x coordinates, right? That doesn't flip-flop. Some people like to flip-flop those because they think we're flipping everything. Nope, once we get these points, you're pulling your transformations from this, just like you did with the exponential. Okay, notice we add h first, then we divide by c, we multiply the y's by a, then we add k. Okay, the one thing I wanted to point out was the vertical asymptote, right? It starts at x equals 0, but since we're shifting it first and it becomes x equals h, then dividing it, unlike the exponential where it just ends up being the vertical shift, this one, because we shift then compress, you're going to have to take both of those into account. So your final vertical asymptote is going to be h over c. Okay, so let's talk about that. The final vertical asymptote is h over c. Then, and the way I figure that out, I don't have that it's h over c memorized. I simply start with x equals 0. Then whatever the horizontal transformations are, I simply apply them to my asymptote, and then it gives me the right answer, right? I don't have to worry too much about memorizing that it's h over c. I can just apply the transformations to it, okay? The range, just like the domain of an exponential is -infinity to infinity always, the range of a log, because they're inverses, is always -infinity to infinity. And then the domain is going to depend on the asymptote, right? If it is horizontally reflected, that's not how you spell reflected, then it's going to be -infinity to the asymptote. If it's not horizontally reflected, your domain is going to be just the asymptote to infinity, because it's going to go to the right forever. Okay? So now I'm going to show you guys two examples, one of an exponential, one of a log. Maybe pause the video and try and do it on your own to see if you know how to do it, and then watch it back. Or if you feel like you are struggling to do them on your own, this video is a good one to watch. Okay? If you run into any questions on these problems, feel free to email. Guys, so I'm going to start by doing an exponential one with all the transformations, and then I'll do a log one next. So to start an exponential function, we always start with the parent function. The parent function is always of the form y equals b to the x. The base is what's being raised to the exponent. It's not a transformation, it's whatever has the exponent on it. So in this case, our parent function is going to be y to the 1/2 x, right? We get rid of all the transformations. It's just simply our base to our exponent, okay, to our variable. That is where I get my starting points from. So I'm going to start just looking at this function, y equals 1/2 to the x, and I'm going to input -1, 0, and 1 into the exponent. So 1/2 to the -1, we know negative exponents give us the reciprocal. So that would be 2. 1/2 to the 0, that's 1. 1/2 to the first is 1/2. Okay, now I have to start looking at my transformations. Okay, so I can see for my horizontal transformations, I've got two things happening, right? I've got 2x plus 10. Remember, for horizontal transformations, we do opposite order of operations. So we're going to look at the addition first, but we also do opposite operation. So not only am I going to look at the plus 10 first, it's actually going to be minus 10. Okay, for my vertical transformations, my vertical transformations are on the outside of my function. So that's my 4 being multiplied and my 3 being subtracted. Remember, for vertical transformations, we follow order of operations and we follow the operation that it says. So the first thing I'm going to do vertically is multiply my y's by 4. Okay, so then I make my next XY table. Okay, and the XY tables, that's how we figure out our transformations, right? Once you're actually graphing that final XY table, it's already done all the shifting, reflecting, stretching, and shrinking. So we don't have to worry about any of that when you're actually graphing it, right? Once you have all your points, you just plot them and go from there. So I'll take all my x coordinates and I will subtract 10. So -1 minus 10 is -11. 0 minus 10 is -10. 1 minus 10 is -9. Okay, then to my y's, I will multiply by 4. So 4 times 2 is 8. 1 times 4 is 4. 1/2 times 4 is 2. Okay, now I move on to my next set of transformations. Now, if there isn't a vertical stretch, you don't do it, right? You just skip it. This one has all of them, so you guys can see all of them. But if it's not there, it's not there. We just skip over it. You don't do it. So you won't always have, all 4 of these, okay? So the next thing horizontally is 2 times x. We do the opposite. So I'm going to do my x's divided by 2, okay? Then for my y's, we do what it says. So I am going to subtract 3 from the y's, okay? And then again, I'm just applying this to my coordinates. So XY table, right, I will divide by 2. Let me move this over a little bit so I have a little bit more room. -11 divided by 2 is -5.5. 10 divided by 2 is -5. -9 divided by 2 is -4.5. 8 minus 3 is 5. 4 minus 3 is 1. 2 minus 3 is -1. So these are my final points. There's no more transformations to give. These input-outputs have to do with, the function I was asked to graph. Okay, the last thing I want to talk about is our vertical asymptote. It starts off as y equals 0. It always starts at y equals 0, and then any of the vertical transformations affect it. Now, multiplying it by 4, 0 times 4 is still 0. Then subtracting 3, so now we know that our horizontal asymptote is y equals -3. So this table of values and this asymptote is really going to help us be able to sketch this graph. So now I'm going to duplicate this so I actually have it down here. I'll put that right here just so we have it to refer back to. And then let's make our graph. So we need lots of negative x's. So I want to go mainly negative on the x's, and then just a little negative y. So we'll draw it like this. And then I will draw my increments kind of far apart because I want to be able to very clearly, graph my 0.5. So we'll go 1, 2, 3, 4, 5, 6. 1, 2, 1. 1, 2, 3, 4, 5, 6. Okay, and now I'll graph my points. So -5.55 will go 1, 2, 3, 4, 5. So we'll go 5.5. Then 5, 1, 2, 3, 4, 5. So they'll meet right about there. So that's where my point will be. Then -5 is right here. Oh my gosh, that's a very squiggly line. That needs to straighten out. There we go. -5 and 1. So that's going to meet right about here. So that'll be my point here. Then -4.5. I'm really bad at drawing those lines up. And -1. It's going to be right about here. Okay, so you should be able to see there's a little bit of a curve to it. Anything that's horizontally compressed, the curve's going to be a little more tricky to see. But you can tell that that's not just a straight line. And the next thing that's going to help us get a good graph going is the fact that we know that the horizontal asymptote is at y equals -3. So I guess I do need to extend this down just a little more so that I can put in my horizontal asymptote. And the reason we need that in there is because that's going to help us connect our points, because we know that our function has to follow along the asymptote, right? It's going to kind of flatten out along it. It can't, some people like to graph these and make it go below, but the whole point of the asymptote is that it kind of squishes your graph. It prevents your graph from going any lower, and then it goes up forever along this curve. I'm really not doing a good job at freehanding these curves, so I'm just going to take it slow. Okay, so here is my final curve for this graph, right? And then I can state, you know, my asymptote is y equals -3. Notice that it is a equation of a line. This is the line y equals 3. You can't just tell me an asymptote is -3. -3 is a number. I need an equation. The domain of all exponential functions is -infinity to infinity, so that should be kind of a free point. And then range, notice it goes up forever, and the lowest, right, we do our range from lowest to highest, so the lowest it goes is -3, and the highest it goes is infinity, because it goes up, up, and away forever. Okay, so that is an exponential function graphed from start to finish. Let's take a look at what we did. We start with our parent function, which is always the base raised to x, and we input -1, 0, and 1 for our x values. Then we applied our horizontal transformations in reverse order of operation and opposite operation. So we did the addition first, and it was subtraction. Then we did the multiplication, and it was division. Then we did our vertical transformations in PEMDAS order and in the operation that they asked for. So we first multiplied our y values by 4 and then subtracted 3. We plot our points, we sketch in our asymptote, and then we follow our curve along it. Then we state our domain, range, and equation of the asymptote. So now we're going to graph a log 1, which is quite similar to exponential. There's just a couple differences at the beginning, right? The transformations are going to work in the same exact way. This idea of inside the function is horizontal and you do everything opposite, still true. With outside the function, you do kind of everything it says and it's vertical, still true. The difference is how we're going to get our starting points. So I'm going to start this off. And I'm going to look at my parent function. My parent function is always of the form y equals log base b of x. And I'm looking for whatever the base is. So here, the base is 4. So that's going to be y equals log base 4 of x. Okay, that is my parent function. There's none of the transformations. It's just the base in the log function, similar to how it was just the base in the exponential for exponential functions. Now what we need to do is we need to use our property that allows us to switch between exponential and logarithmic functions to be able to actually graph this, right? To have inputs and outputs. So we've got y equals log base b of x. We know that that is equivalent to b to the y equals x, right? We could technically, I mean, it is a function. Your calculator, a very fancy calculator, could evaluate things if you input it into the log function, but we don't have fancy calculators. We're going to act like the fancy calculator, and we're going to do that by inputting into the exponential version of the function. So I'm going to rewrite y equals log base 4 of x as 4 to the y equals x. Okay, these two things, they are equivalent. And now I have something I'm familiar with, right? I know how to evaluate an exponential rather than inputting in for my x coordinate, though, because that wouldn't be helpful, right? I'd still have to solve for it, not really evaluate. I'm going to input into my y coordinate. So I'm going to plug in the same values I did for the x coordinate in an exponential. So 4 to the negative 1, that's 1/4. 4 to the 0, that's 1. 4 to the first is 4. Okay, now I have to apply my transformations. Okay, so if I look inside my function, reverse PEMDAS, I'm looking at the subtraction first, and I always do opposite operation for my horizontal transformations. So I'll do x plus 3. Okay, for my vertical transformations, I follow order of operations, so I'm looking at this multiplication first instead of the addition, and I'm going to do the operation given, right? I always follow what it says for vertical. So I'll do y times negative 2. And now I just need to actually apply that here to my x and y coordinates, and that'll give me the next ones to work with. So let me move that over a bit so I have room. So we'll have 1/4 plus 3. I'm going to write it as a decimal. 3.25. Then 1 plus 3 is 4. 4 plus 3 is 7. Okay, I multiply my y's by negative 2. That's going to be 2 times negative 2 is 2. 0 times negative 2 is 0. And 1 times negative 2 is negative 2. Okay, then what I'll do is I'll look at my next set of transformations, right? You're not always going to have every single one. In this case, I do, because I wanted to show you guys all of them. But if you don't have it there, right, if there was no h, then I would just skip it. I wouldn't do it. I'd move on to c. You're only doing the transformations that are there for you in your function. So the next thing I see happening is I have x times 1/2. So my next transformation would technically be, right, to divide by that, because I always do the opposite. So I'm going to divide by 1/2. That looks a little clunky though, right? So remember, if you divide by a fraction, that's the same thing as multiplying by its reciprocal. So actually in this case, what we're going to be doing is 2 times x. You could also divide by 1/2 in your calculator, but I personally think it's a little bit easier to think about as multiplying by 2, right? And then my y coordinates, I just do what it says. So it says to add 1 on the outside of the function. So it's a vertical transformation. So that is what I'm going to do. I'm going to add 1 on the outside. Okay, and then I can create my last table of values here by taking 3.25, multiplying that by 2, that's 6.5. 4 divided by 1/2, or 4 times 2 is 8. 7 times 2 is 14. Okay, y plus 1, I'll have 3, 1, and negative 1. Okay, those are my points here. The last thing I'm going to do is kind of transform my vertical asymptote so you guys can see where that comes. So remember, your vertical asymptote always starts at x equals 0 for the parent function, right? This function right here has a vertical asymptote of x equals 0. Then I'm just going to apply my transformations that happened to x, right? Because it has to do with my x's. So I'll add 3. This point, it's x equals 3. Then I multiply by 2 or divide by 1/2, and that will give me that my vertical asymptote is x equals 6. And it's helpful to have this and do it algebraically like this, so there's really no questions. I don't have to guess what it is. I can put it on my graph, and then I'm able to clearly see what's going on here. So let me copy this, and then we will get our graph going down here. Oh, did not mean to do that. There we go. So, looking at this now, I can put my graph together. I'm going to pull a different color. Don't mind me. And I need to go really, really far in the positive on my x's, and then just a little bit in the negative for my y's. So let's mark these off. I don't really need my increments to be that far apart, because I'm not really graphing too many decimals close to each other, right? So I'll just do it so I can fit it. Okay, hopefully I made it out to 14. I feel like I did. And now let's just graph our points. So we'll start with 6.53. So 1, 2, 3, 4, 5, 6. So 6.53 is going to be about here, or 6.5. Oh, why is there an arrow on it? I've actually never had that happen before. There we go. And then 3 is here, so it's going to meet right here. Get rid of those. Oops, I got rid of that. Didn't mean to do that. There's my point. Okay, 8. That's 6.578. I'm going to be like right about here. 1, I'll be here. So there's that point. Then, last but not least, we have 14. Goodness. 9, 10, 11, 12, 13. 14's here. Negative 1's there. So my point's going to be right about here. Okay, and this one you can really see that it curves, right? Log functions usually have kind of more obvious curves. Let me put my vertical asymptote in there because we're going to need to follow along that, right? Our curve always kind of follows that. So here we go. At x equals 6, right, which means x is always 6. It's a line through x equals 6 right here. Then our curve, right, it's going to straighten out along the asymptote. You know, if to the naked eye, it would be, you wouldn't be able to tell. It'd be so close, it'd be touching it. But for what we're trying to graph here, you know, we can only do so much because it's getting infinitely closer and closer. And then it's going to curve, right? You can see it's got a curve here, and then it's going to go over and down forever. You want to be careful. It can be tempting to have like a horizontal asymptote here or think it straightens out, but really it is going kind of down forever in that direction, right? It's not curving over completely again. Okay? We've already, as far as characteristics go, right, we already have that the asymptote is at x equals 6. Remember, that's an equation of a line. You don't just say 6. What does 6 mean? X equals 6 is an equation of a line. The range is always, for log functions, negative infinity to infinity. Okay, because it's going up forever, and it's a little slower going down forever. And then my domain, my furthest, my leftmost point is 6, right? It never goes lower than 6. There's no function over here when x is less than 6. So it starts at 6, and then it goes to the right forever. So 6 to infinity is my domain here. And we're done.